Okay, so let me start. So today's title is Concept of Washboard Potential in Josephson Junctions, and this will be derivation of washboard potential in Josephson Junctions. So that's next lecture, which comes after last lecture, where we have seen certain solutions of RCSG model to fluid model. So brief reminder is as following. Okay, so this is standard picture how the theory of superconductivity and superfluidity develops, and there is certain development of theory and also experimental developments. So we are right now on the level of 9050, pretty much, actually, just on a little bit before that. So this is the Ginzburg-Landau theory is not yet introduced. It will be introduced next couple of lectures. So yeah. Okay, so let me move on. So basically, this is the picture of Josephson effect. So we have two quantum systems that are interacting in perturbative way. So this is like this tunneling of Cooper pair via insulating barrier or via some narrowing is manifestation of perturbative interaction. So basically, it's being assumed that left side was Einstein condensate and right side is both Einstein condensate. And there is a tunneling between those two condensates in such a way that there is so the state left and right state is slightly perturbed. So this is there is presumption that on the left and right quantum state we have macroscopic quantum effect. So we have macroscopic wave function, and in case of superconductors, this wave function is expressed by phase theta L, and there is density of Cooper pairs, square root of density of Cooper pairs. So that's how it is expressed, left and right. Then simply saying we have the phase difference that will play important role in the system physics equations of motion, but basically the phase difference is supposed to be seen as a Haranov-Bohm effect. So basically, there is a phase imprint on this system, and this phase imprint is by a Haranov-Bohm effect by vector potential presence, essentially. So the whole system will be driven by magnetic field, and this is very much driving factor. Okay, there's something. Yeah, so do you see my slides? Wojciech?
Yes.
All right. Something was coming. Yeah, all right. So then there is this Hamiltonian for left and right quantum system and for tunneling form. So we have this EL, ER, and tunneling form in equation number 2. And then basing on that Hamiltonian from equation 2, we can arrive to equation number 3. In this equation, you see this is very much equation 3. It's a nonlinear pendulum equation. So it can be linearized if phase difference is of small value, like below 7 degrees. Let's say you can replace sine theta with theta, and then basically it's a pendulum equation, second order differential equation. So there will be certain analogy with pendulum system, and the total current flowing via Josephson junction is nothing else as this this IT. So this current will go via two different channels, non-dissipative channel, which is and dissipative channel. Dissipative channel is this R presence, and there is a Josephson, so there's superfluid current flowing and current of normal particles. So basically those three RTSG model is reflected by equation 3. When you move from, so insulator is expressed by capacitance, and lack of capacitance is like dropping of this term. So then we have weak link type Josephson junction. Well, then we can describe actually the Josephson effect by hierarchy of different models, but we are just now touching the very bottom of it, and then we will move towards more refined description. So we here there is also a class of systems that could be studied. So this is like weak link on the left side and tunneling on the right side. So so here is the case of superconductor ferromagnetic strip on the top. So so here basically we can postulate the existence of these 4 circuit elements, which are all dependent on the level of magnetization of this ferromagnetic bar on the top. Right, and there are certain regimes. So that's how it is. All right, let me move on. So then there is this Andrew-bound states existence in Josephson junction, which gives most generalized picture. That this will be accounted later, not now. So basically we have demonstration of CPT symmetry. So simply saying electron coming from normal metal into superconductor is reflected as a Hall, and then it generates moving Cooper pair. So and also reversely, Hall coming to hit the superconductor is reflected as electron, and then the movement of Cooper pair is implied. So this is so-called Andrew-bound state inside Josephson junction, and this Andrew-bound state is how to say very much essence of Josephson effect. This under-reflection is prominent when the energy of electron and the Hall is of small value. Yeah, so that's how it is. And then there is a charge conservation, momentum conservation, and energy conservation during this process. And there is manifestation of CPT symmetry, because you can interpret moving Hall as moving anti-electron in a very real way, since electron and Hall can recombine, or we would say recombination is a bit similar to annihilation process. All right. There is this always manifestation of those 3 effects in Josephson. So Josephson effect is presence. There is AC Josephson effect, and there is single electron transistor effect that also can be manifested in Cooper pair box, and there's a quantum Hall effect. All right. So I have already mentioned that you can basically search for existence of Josephson effect in case of systems where there is a macroscopic wave function. And so this is, for example, Bose-Einstein condensates that are coupling, and also have the presence of Josephson effect. You need to be aware that the Bose-Einstein condensate takes place It's nano-Kelvin regime, which is significantly smaller than milli-Kelvin regime. And this is usually achieved for thousands, a couple of thousands of atoms. So that's not, the system is not that easy to be used as on massive scale, since this process of achieving Bose-Einstein condensates is quite sophisticated. So those systems are not really regarded as real candidates for a quantum computation. Well, some people would claim so, but they are not. So then basically we are kind of forced into usage of Josephson junctions, that's our top interest on it. Well, then from experiments on Cooper pair when you have ferromagnetic strip on the top of superconductor, you can get such IV characteristics which indicate the existence of weak link. And then this is Luis Gomez data, and there is a presence of Shapiro steps if you place external antenna. If you place external antenna with microwave signal, here it's 2 gigahertz signal, then suddenly, instead of this black, you see this, then you can have this, instead of black, you have blue, strong blue steps, Shapiro steps. And then you can characterize them by having this dV over the I. So you see that they behave basically in that way. So so this is the case of existence of Shapiro steps. So this is experimentally generated IV characteristics for a weak link. On the other hand, if you have this tunneling Josephson junction, you basically deal with such type of structure. Okay, so let me move on. There's something. I don't see my slides. Yeah. Do you still see my slides, Wojtek?
Yes.
Okay, because there was some problem with my. Yeah, I need to see why I am not in full screen mode anymore. Yeah, I don't know right now. Yeah. Okay. And then we have already accounted for derivation of Josephson effect. So so basically we have two equations, coupled equations as 2.16. So and this is basically equations which are derived from this the equation number 2, essentially. So this is 2.16, and then this is already what we did. It's we come into equations DC and AC Josephson junction equations, which express DC Josephson junction effect. So the current flow is proportional to phase difference. This is equation 2.21. And then the second equation is that applying small voltage across Josephson junction would generate phase difference oscillations. So this is, in a sense, voltage control signal generator. So yeah. Now I want to state the essence of I want to come to this washboard potential concept, and essentially we start from this two fluid model. So then the total current flowing via the system is given by IT. So this is voltage over resistance, then plus I sine theta plus C d over dtV. So this we can rewrite it using this AC Josephson junction knowledge. Then this voltage is expressed by derivative of so basically H over 2E d over dt theta is voltage. So doing so, we arrive into equation 2. So the total current is then so this is basically pendulum type of equation 2. And under the constraints of resistance going into infinity, so let's say, or we neglect this dissipation channel presence, so we can drop the first term. So this term can be dropped. So we come into equation 3. And in this equation 3, we have simply two terms. So remember that you can control by phase by imposing total current source with time. So you can have those two terms. And then there is a certain trick we are going to do. So we will at first imply that total current flowing is constant. This is IB. And then we multiply both sides by d over dt theta. So doing so, we have the equation number 4. So we have simply the presence of first and second derivative on the very right side of this equation. And the presence of first, second derivative might suggest this is d over dt over theta square. And this is indeed what we can recognize is that so you see, if you place everything on one side, so equation 4, so you move this term to right side and there will be 0 here, then you can write that such relation occurs. That 0 is equal to d over dt minus I cosine theta and this square and this minus IB theta. Do you agree, Wojtek? Do you agree that such situation takes place?
Yes, I think so.
Because this is very much, in a sense, very much similar to the case of deriving this energy conservation principle from Newton equations of motion, right?
Yeah.
So basically the conclusion is that there is d over dt over such expression, and this expression is so there's a postulate that I'm just a little bit, so there's equation 5. So everything what is in the square bracket is constant. So there is d over dt over E like energy. So so this we will propose that this is total mechanical energy, whatever is written in this bracket. Yeah, is it intuitive somehow, Wojtek? Is it intuitive?
Yeah.
All right. So this postulate will be that Hamiltonian is of the following form: I0 1 I minus cosine theta. So just see I just added a constant to this. Of course, if I add constants to E, it still will be valid, right, Wojtek? Because if I add any constant,
Yes.
this will be valid. Yeah, so I basically have written 1 minus cosine theta minus IB plus this term, which is written here. So this is constant. And so we can hypothesize from this kind of general way of thinking that very right side is kinetic. So theta is like position, right? So theta is like position from classical mechanics. So this phase difference across Josephson junction is like position, your generalized position. So doing so, we have this d over dt. Theta is derivative of position with respect to time. So this is like velocity square, right? And then theta is, so there is some nonlinear potential over here. So in total, we can associate the meaning to this term, which is of as following. So this is this meaning. So this is like kinetic energy plus potential energy. So we define new quantity U of theta. So we have this 1 minus cosine theta minus IB theta. And such term is nothing else as washboard potential. So this is called washboard potential, and it has certain you see there is a slope, because if there is no this is if beta is set to 0, IB is set to 0, then this will be periodic function. But there is a slope. Slope is controlled by IB. And there are certain, so there's 1 minus cosine theta. And so this is nonlinear. And there is depth of this oscillation. So you see depth of these oscillations is regulated by I0. I0 is nothing else as proportional to critical current of Josephson junction. So this depends on the size of Josephson junction, for example. So so this is this washboard potential that exists in literature, and basically we have we need now to think how to quantize it, or if there is a possibility of its quantization of such system. But before doing so, I believe that I also should mention about one phenomenon. So basically, we have the oscillations back and forth in a classical picture, right? Back and forth. Like, do you see my mouse pointer?
Yes.
Right. So, but in classical mechanics, you cannot tunnel. Essentially, perhaps if you add noise, you can jump. But if you don't reach certain magnitude of oscillations, you cannot tunnel. But from quantum perspective point of view, if you approach to this point, let's say, there is very much non-zero probability of tunneling into another well. So there is a so-called macroscopic quantum tunneling that might happen in the Josephson junction. Yeah. So I'm just indicating this phenomenon. All right. So let me move on. And from last week, actually from last 2 weeks, due to long vacation period, we have this picture of existing analogies between pendulum and Josephson junction was very much pronounced. And then there is proportionality between capacitance and moment of inertia. And then there is conductance versus viscosity coefficient, phase difference and angular position, and so on, and bias current and applied torque, which means external force pretty much. Yeah, so then there is a voltage and angular velocity. And there is a Josephson current, and there is horizontal displacement. So you see, there is a lot of analogies with classical mechanics, but if there is, let's say, quantum features present in the system, you would expect macroscopic quantum tunneling to take place. All right, and so this is so far, I believe, so clear. I want to mention that there are various types of this tunneling Josephson junction. So superconductor, insulator, superconductor. And so this is the tunneling Josephson junction. You can see the thickness of insulating element can be 10 to 20 angstrom. Then you can have proximity Josephson junction. So there is superconductor, normal matter superconductor. There is constriction or microbridge. And there's a point contact in Josephson junction. Yeah, so this is just to let you know on different possible features coming from those different 4 types of Josephson junction. All right, now let me talk a little bit about this procedure of quantization of Josephson effect. Yeah, so there is a Poisson bracket definition, and let's say I try to, yeah, okay. Okay, so we have this, we have phase space, position and momentum, and you have 2 functions that depends, f and g, that depends on the phase, space. So there's pi, qi, so momentum, and q stands for generalized position in a phase space. So we have f and g Poisson bracket, so-called. It's formally defined by this sum. So this is df over dq I dg over, so QP, so just this order QP, first position momentum, derivative, and there's FG the same order as here, and there's minus, and then you have the same order F and G, but different order of derivative than PI QI. So this is formally the mathematical object known as Poisson bracket. This Poisson bracket now could be referred to some more practical cases. So this is, you can have Q and QK, QL, in the Poisson bracket. So then if you apply for two coordinates, like, you know, x1, x2, x3, or just x, y, z. So then you, after conducting these computations, you see that it's set to 0. So, and the same thing occurs for Poisson bracket between PK and PL. PK and PL. It's also set to 0. And then you can compute the Poisson bracket between QK and PL. And actually, when you do so, you get such formulas here. And then, so this is consequently, and what happens is that, yeah, the QK and QI, this is Kronecker delta. This is also Kronecker delta. And there is no chance those things can be dependent on each other. So this is set to 0. But anyway, such type of two deltas, QKI, QLI, are only equal to KL. So, and this is very, very prominent observation because suddenly it turns out that this Poisson bracket has the same features as commutator known in quantum mechanics between x and p, the position and momentum, x and px, y and py, z and pz. So this is actually very much formalized in that way. So doing so, we see that somehow, and this Heisenberg principle can be present in over here. If we formally replace Poisson bracket with commutator operator, and then, so there are certain steps towards quantization procedure. So before going further, we observe certain properties of Poisson bracket. And this is Fg minus Gf. So there's anticommutativity for both, or obviously. There is certain bilinearity. So this is like, we have linear combination of F and G operators. So there's A and B. So you have simply such expressions as over here. And the same stands if there is, for such Poisson bracket, H and A times F plus B times G. So you have things like given over here. Then there's Leibniz rule, which is like that. So this is FGH and then FHG. So, and there is also Jacobi identity. Jacobi identity is that you have F. It's like nested Poisson bracket, GH, and then there is F. So this is done like that. And if you look on this commutator properties, they have plenty of them as specified over here. So there's ABC is ABC And this is what we already have seen before. So this is pretty much this one. Yeah, or this one. So then of course there is more and more. You can simply determine on your own those things to be you can derive them actually with careful studying. So that's how it is. So, and this profound analogy can be used for quantization, for setting the quantization procedure. So essentially we have this equations of motion that can be obtained from Poisson brackets. So how to deal with that in greater detail? So derivative of d over dt on Q is d Hamiltonian over dp. So this is standard Hamilton equation of motion, but it turns out that that's result of Poisson bracket of Q or just one of the space coordinate versus the whole Hamiltonian. And actually this is, and p d over dt over p is minus h over d over dq. So this is also Poisson bracket of p and h. So this is standard procedure of getting the equations of motion from classical mechanical system, right? And then how to go into deeper way. Okay, and then there's canonical quantization procedure, which was also pointed out by Dirac. So essentially Dirac has, and inventors of quantum mechanics has observed that, remember, the Poisson bracket of position x and p was shown over here, and this was set to 1 for let's say k equal to l equal to 1. So it turns out that here it is set, this is commuted. So for the commutator between x and p is equal to I times h bar. So it's very much like constant, but this is normalized times I-O times h bar. So because of that, so there is, let's say you have certain theory, and you want to impose, so it's very tricky that commutation relations are built in Poisson bracket formula, even into classical mechanics. So if you deal with Poisson bracket equations of motion expression, then it's very easy to quantize the system. So if once you have Poisson bracket between A and B functions or operators, then you replace is 1 over h bar Poisson bracket between A and B, and that's it. So you get equations of motion in quantum case in a way, right? All right, so let us do it. And then this is very short slide, how to think. This will be prolonged later, how to deal about the procedures of thinking in that direction. So yeah, so this is, I already mentioned too that we can establish the Hamiltonian once we omit the dissipative channel. We set resistance into infinity. Actually, we can also think about having two superconductors separated by vacuum in such case. There will be no resistance. And the electrons also can tunnel. All right, so you have 1 minus cosine theta. So this is the washboard potential minus EIB theta. So this is washboard potential, and this times this kinetic term. How to move into quantum way of thinking. So then we rewrite this equation into such a form as given here. And then there is C1 over KE, this H bar, and then we take H bar to the square. Is this correct, Wojtek? Is such way
Yes.
It's clear.
Okay, it's correct. Fine. Then we move to next level. So 1 minus cosine theta minus B. And then the claim is that let us think about this term that is inside as momentum, P theta, right? Square. Wojtek, do you agree? That we can
Yes.
write like this? Good. Then this, so we already have equation of motion, because here is like a velocity square, and then here it's by theta and momentum, right? And then this, you want to be sure that this momentum which you are using is nothing else as that this p theta will commute with theta, right? So then you replace this momentum p theta with h over I d over d theta. Do you see this?
Yeah, I think so.
Because that's the way of doing. So this is very much analogical to Schrödinger picture in position, Schrödinger equation in position representation, right? So so that's it. So then you end up in an effective Hamiltonian that's very much like Schrödinger Hamiltonian, right? So this is Schrödinger Hamiltonian, but with very specific potential of such form. Yes, this is anharmonic potential essentially. This is nonlinear function in total way of thinking. Yeah, because we have even powers in cosine theta has 2, 4, 6 this powers of theta, right? So basically this is anharmonic in very general way. Is it Wojtek, is it clear to you?
Yeah.
Is there any questions from the audience? Yeah, and then there is standard literature. So if there is no more questions, I will simply ask you to sign the list of presents today, and that's it. So you can write on the chat. Right. So I suggest then we finish, we conclude the lectures right now. And